Hey everyone, welcome back. So in this video, we'll be talking about maximum likelihood. Now, in all honesty, the topics we're going to cover in this video and the math we're going to cover in this video have been covered across several past videos. It's just that they haven't all been covered together, and now that we're kind of talking about Bayesian statistics, I thought it would be nice to have all of these topics packaged together into one video. That said, I will link the previous videos that have a little bit of these topics here and there in the description, so you can watch the videos on only the sigmoid function or only logistic regression if you want to think more about those. Okay, so as always on this channel, let's get started with a real-world example. And I've used this example a lot, but let's just use it one more time. I'll try to switch up the examples a little bit later videos, but the example is that we're trying to predict if a student gets into their top choice medical school. So as always, with data science, we have some kind of matrix of data. So X is all these different data points about a given student. So we have n rows, which is n students, and we have p columns, p predictors for each student. These could be things like their GPA and their MCAT score, extracurriculars, how many years of work experience, on and on and on. Stuff that might help us predict whether or not they get into their top choice medical school. And that decision, that outcome, is given by the response variable y. So y is a n by 1 vector, which contains 1 if the student gets into their top choice school and 0 if they do not. So this is a binary classification problem, and one of the first tools we learn to deal with this kind of problem is called logistic regression. So let's go ahead and dive into logistic regression. And this video, as you can probably tell, gets a little bit mathematical. But that said, I have several statements on the board along the way so that whenever there's an equation, we're not looking at it as a series of symbols and numbers, but we're looking at it as a story. So we'll build up the story, and then by the end we'll fully understand why maximum likelihood is important as a tool in solving this very real-world problem. So I'm assuming you have a little bit of understanding of logistic regression. Again, the idea is that we are modeling this quantity, the natural log of p over 1 minus p, where p is the probability that a given student gets in to their top choice medical school. So if p is around 0.9, there's a high chance they get in. If p is like 0.1, there's a low chance they get in. So we're modeling this quantity, which is often called the Logit P. So this is called the Logit Transformation. We're modeling this as a linear combination of all of these data points for the student. So we have some intercept beta naught plus beta 1 times x1 plus beta 2 times x2 all the way to beta p times xp. So this idea should be kind of familiar if you've studied logistic regression before. Now, as I said before, we can write this quantity here more simply as logit of p, just to kind of clean up our equation a little bit. And we can also clean up this right-hand side because, as we said, it's just a inner product, a dot product, a linear combination of all of the data we have for any given student, x. So I've collected all of these beta terms into this vector called beta, and this is just the dot product of beta with x. A small note, I've also put this intercept term into this beta vector, which means that I've had to slightly modify this x so that the first element is a 1, and then after that we have all p predictors. So if you want to be really detailed about it, beta is a p plus 1 vector because it has beta 1 through beta p and also beta 0, and x is also a p plus 1 length vector, where the first element is a 1, followed by all the actual data for that student. That's just a small note. Now we need to kind of invert this equation. We need to solve for p by itself in order to continue on with this maximum likelihood. Turns out it's not too difficult, and what we get back is this form, which if you've watched my video on the sigmoid, you know this is just the equation of a sigmoid or an S-shaped curve. So we're saying that the probability that any given student gets into their top choice medical school is given by this function. And instead of really worrying about the mechanics of this function, just look at what terms are in there. This is a function of beta and x. Another way of saying that is we are going to model the probability that you get into your top choice medical school by looking at all these data points about you, as well as beta, which is driving the structure of this model. So these two things together are going to help us predict whether or not you get it. So this is the form of p, the form of the probability, and let's continue on from there. So let's kind of just break down that last equation a little bit further and see if we can't work with it to get to our maximum likelihood. So for any given student xi, so xi is again just a student and all the data about that student, GPA, MCAT score, whatever. What's the probability that that student does get into their top choice medical school? Well, we literally derived that by definition right here. So we can just write that again. We can say the probability that this given student gets into their top choice medical school is going to be e to the beta transpose xi over 1 plus that same quantity. Fair enough. We can also write that in blue here as this quantity, which looks very similar to the thing on the left-hand side of the equal sign. The only difference is that I've put a yi in front of the exponent here. Notice it doesn't actually change anything, because in this case, if they do get into their top choice medical school, that means yi is equal to 1. Therefore, I'm just multiplying the exponent by 1, which is like doing nothing. So the question arises, why would I even do it? We'll come back to that in just a second by looking at the second case, which is what's the probability the student does not get into their top choice medical school. Now notice this is a binary classification problem, so there's only two outcomes, which is good news for us because it means we can just take 1 minus this guy, which is 1 minus the probability you get in order to get exactly the probability you don't get in. So that's what we do here. This quantity you can get by just doing 1 minus this guy, and you can even do a quick check to make sure those two quantities add up to 1. Their numerators, 1 and e to the beta transpose xi, exactly add up to the denominator. So indeed they add up to 1. This is valid math. Now, the interesting thing is that even though these look slightly different, we can write them in the exact same format. We can make the same logical step going forward. What I mean by that is that we can write this quantity here as e to the yi beta transpose xi divided by that same denominator. Why does this work? Because in this case, we're talking about the probability that you get rejected from your top choice medical school, which means your yi is equal to 0. And when we put a 0 up here, e to the 0 is equal to 1, which exactly means that these two quantities are equal to each other. But more importantly, notice that we have kind of formed a connection. We can get this probability that you get accepted and this probability that you get rejected looking in the exact same form by just including yi, which again is either 1 or 0, into that equation itself. This is going to be very helpful in formulating the maximum likelihood, which comes next. But before we go to formulating the whole likelihood for all the students, let's just pause and make sure we understand intuitively what it is we have now. So we have that probability of yi again being either 0 or 1, so the probability that the student gets in or does not get in, given information about the student, which is xi, and given the parameter vector we're currently dealing with, which is beta, is equal to e to the yi beta transpose xi divided by this denominator. And so what we basically did in this equation is combine both of these cases, and we showed that we can get them both looking in the same form, which are written in blue here, and that form is exactly what I've copy-pasted right here. But forget the math for a second. Intuitively, what is this quantity that we're looking at? We're saying that the probability of observing the actual yi given some students xi and given beta is this. And to elaborate on that a little bit more, let's say that you're a student who fortunately did get into their top choice medical school, so your yi is equal to 1. We would ask the model, what's the probability of observing that event in the world? We would plug in yi equals 1 into this equation, and we would get exactly the probability that you get accepted. So what we're kind of doing is trying to get a matchup between the actual things we observe in the world, the students who do and do not get in, and the probability that our model would assign to these outcomes. So just to finish the story off there, we told the first part, which is that if you do get in, we plug in yi equals 1, and we get the probability that the model would say you get in, and we hope that's high, because you did in fact actually get in. Now, if you unfortunately get rejected from your top choice medical school, that is an observed event in the world. That did happen. And we would love for our model to pretty closely model that, give you a low probability, so that would tell us our model's doing well. How would we get the probability that you don't get in? We would take 0, which is what actually happened for you, plug in 0 here, and we would arrive back here, which is the probability that you get rejected from your top choice medical school. So I've said a lot of words, maybe I've said too many words, but what I'm trying to convey to you is that these equations are helpful, obviously, but they're not really the point of the story. The point of the story so far is that we're trying to build up some kind of nice model whose probabilities closely align with the actual outcomes in the real world. That is, if a student did get in, we want the model to output something high. If the student did not get in, we would love the model to output something low, because now our model is aligning with the reality of the world. Keeping that framework in mind, let's press on to the end of this video. So again, everything we've said is for one student. We said in the beginning for any student xi. So how do we extend this logic to all of the students? Well, first we make a maybe realistic assumption, maybe not realistic in some cases, that each student's probability of getting into their top choice medical school is independent of the others. Now, I will admit that in this case, probably admissions are correlated between students, but just to keep things kind of simple, and this is the assumption that a vanilla logistic regression is going to make, let's make that assumption. So we say that the probability for every given student getting into their top choice medical school is independent. So now if we ask a broader question of what is the probability of seeing all of the outcomes in this data, all n outcomes in this data, that I actually see, we can simply just multiply the probabilities for all n students together. Again, this is from the independence assumption that we are making. And what does that look like mathematically? We write this usually kind of fancy L for likelihood, but you can just replace that with a probability sign. It's really the same thing. We're saying that the probability of seeing all of these outcomes, notice there's no I subscript on this Y, which means that we are saying the probability of seeing all of these outcomes, this student got in, this student didn't get in, this student didn't get in, and so on, all these n outcomes, given X, which is this big data matrix of everybody, all the students, and given beta, that's the same parameter vector we've been working with this whole time, the probability of seeing those outcomes is given by the multiplication of the individual probabilities for all students. That is probability of y1 given x1 and beta times probability of y2 given x2 and beta, all the way down to probability of yn given xn and beta. And again, just kind of abstracting away from the math for a second, I think these multiplication signs are much better understood as and symbols, which means that this is the probability the first student has the outcome that we see, times this is the probability that the second student has the outcome that we see, and we multiply all these together. And naturally, based on everything we said, we would love for this quantity, called the likelihood function, to be as large as possible. The reason we want this to be as large as possible is because we want each of these individual probabilities to be as large as possible. And backtracking, why is that? Why do we want the individual probabilities to be as big as possible? Because the individual probabilities are measuring what's the probability of a given student having the outcome that we actually observe in the real world, whether that outcome is a accept or a reject. Okay, so that's the whole story, and that's probably the hardest part of this video, is not the math, but the understanding. Understanding that the likelihood function is basically the sentence, this is the probability of seeing all of the real world outcomes that I actually see in my data. And if my model is good, I would expect the probabilities output by my model to all the time closely match the actual outcome, whether that's assigning a high probability to accepts and assigning a low probability to rejects, which means that this overall quantity would be very high. All right, so the last part of this video is, of course, we have this likelihood function. We want to maximize it. We know that now. How would we go about doing that? Maybe there's a nice closed form if we just take the derivative. Now, before we take a derivative, let's do one very common step, which is take the logarithm of this likelihood function. This is not a step we do for mathematical reasons. This is a step we do for computational reasons. Notice that what you're looking at here is the product of n probabilities. And probabilities, even large probabilities like 0.9, if you multiply enough of those in a row, it's going to go to 0 or something close to 0 really, really fast. So the computer usually runs out of precision, and even if this gets arbitrarily close to 0, it'll just send it to exactly 0, which means that our entire problem is going to break. So we know that the log maintains the order of things, so maximizing a thing is equivalent to maximizing the log of the thing. So we're going to just take the log of this, which I do down here, so log of this likelihood function, and we know that a log applied to products breaks that product up into sums of logs. Okay, so if I take the log of the left and the log of the right, I get the sum from I equals 1 to n of the log of these individual probabilities. Again, this is a very common, very needed computational step. And the last step we're going to do is now we can take the derivative of this log likelihood and maybe try to set it equal to 0 or do something with that. And that's the last thing I'll show you in this video. I won't show you all the gory details of that, but I'll just show you the high-level steps. So we have this quantity, and we can break it up better to look like this. How did I break it up to look like that? Notice that the inside probability is given by this form right here. So if we take the log of this form right here, we can use further rules of logs, which means if you take the log of a quotient, it's the log of the numerator minus the log of the denominator. If I take the log of the numerator, we see that it's the log of e to the something, so I can just bring that something down. That's exactly what you're seeing here. This guy is the exponent you see here. And remember, all that minus the log of the denominator. The denominator looks like this. That's exactly what you're seeing over here. So take a second, piece of paper, just stare at the screen, rewind a few seconds, and make sure that you understand that this guy can be written just like this. And now what we'll do is take the derivative with respect to beta. And before I do that, let me just kind of frame this problem one more time in terms of knowns and unknowns. There's kind of three quantities that have been floating around this entire video. We have x, which is the data matrix. We have y, which is the outcomes. And we have beta, which is the parameter vector. Which of these are known? X and y are known. We have this data. We literally have it. The only thing that's unknown in this problem is beta. And so the goal of this problem, I probably should have said this a few minutes ago, but the goal of this problem is to get a good parameter vector beta. And what do we mean by good? Good in the sense that if we pick that beta, the probabilities that are output by the model are going to closely match the truth. Another easier way of saying that is that I want to pick a beta such that the likelihood function gets maximized. That's exactly what we're doing now. We're going to take the derivative with respect to beta. So derivative of the log likelihood with respect to beta, we get this form. Again, I'm not going to go into the details there, but you can check that for yourself. And then we can combine this so that it looks like this matrix form. And I'll also choose to skip the details there just for brevity. So we get that x transpose times the quantity of y minus sigma xb. Let's pause for 2 seconds. What is sigma xb? Sigma xb, as I've said here, is the probability that the student is going to get accepted given this information about the student and given this parameter vector beta. Let's abstract away from the math again just for a second and think about why this form of the derivative would be indeed something that we want to set equal to 0. What does it mean to set this equal to 0? Well, it would mean setting this inner part, this y minus sigma so-and-so, to be as small as possible, to be as close to 0 as possible. And why would we want that to be as close to 0 as possible? Well, let's follow the logic here. The first part of this is y, which is either 0 if the student gets rejected, 1 if the student gets accepted. The second part of this is the sigma function, which again, more simply said, is the probability that the student gets accepted into their top choice medical school. So this y is a big vector of students. Let's say the current student we're looking at is 0, which means they unfortunately got rejected. What would we want for the probability? We would want the probability to be as close to 0 as possible. So the corresponding entry in this other vector, this other n by 1 vector sigma, should be also something small. Now on the other hand, if some entry in y is equal to 1, which means the student got accepted into their top choice medical school, we would want the corresponding entry, the one that lines up with that, in sigma to also be very high, maybe 0.9, 0.99, something really high, so that when we subtract those two numbers, the 1 from the y and the 0.99 hopefully from the sigma, we again get something really small. So besides mathematically, more importantly, intuitively, this does make sense as a quantity that we would want to have very close to 0. Because this quantity is basically, well, at least the second part, is measuring what's the distance between the truth about each student and the predicted probability for each student that they're going to get in. And if these things are usually close, we should have a vector of differences that's pretty close to 0, okay? And now this is the bad news part of the video, which is that there's actually, unfortunately, no closed form for the maximum likelihood problem. And by the way, this entire problem we formulated is called the maximum likelihood problem. And the ideal beta vector, the ideal parameter vector, if we could find it, would be called the maximum likelihood estimator, or the MLE estimate of beta. Now going back to the bad news, we don't have a way to get the closed form for beta here. Notice that beta currently is trapped inside of this sigma function, and we don't currently have a way to kind of extract that, get beta by itself equal to some nice closed form that we have similar to in simple linear regression, the ordinary least squares problem. But that doesn't mean it's impossible to solve. In fact, it's relatively easy. With the computational power we have nowadays and statistical methods like gradient ascent, we also have the EM algorithm, for example, if you're familiar with that. So there are definitely methods we can do to try to set this derivative equal to 0, which again is equivalent to getting the maximum log likelihood. But the solving of this wasn't the main part of this video. The main ideas that I wanted to get across is that the maximum likelihood problem really stems from asking the question, what is the probability of seeing the outcomes that I actually see in the real world? That is the sentence that leads us to this equation, and from there everything follows. And again, the groundwork for this equation is laid in the first part of this video, where we were talking about what's the probability that an individual student does or does not get into their top choice medical school. So hopefully you guys learned about the maximum likelihood problem. This was obviously more mathematical than many of the other videos, but I think it's nice, since this channel is called Ritvik Math, to sometimes throw a little bit of math in there just in case y'all are interested. So if you have any questions at all, let me know. Hope you learned something. Please like and subscribe for more videos just like this, and see you next time.